My name is David Swiderski. I'm Senior Technical Strategist with HCInfo, and I have about 20 years of high purity water and field experience. What is the AAMI ST108 standard? This particular standard became an ANSI standard back on August 4th, 2023. It defines various levels of water quality suitable for various stages of medical device processing that will ensure or make those devices safe for patients. It also avoids damage from corrosion and scaling of instruments. Some of the devices that are included are AERs, or automatic endoscopy reprocessing equipment, medical washers, ultrasonic sterilizers, autoclaves, and local steam generators. I also wanted to point out that this became an FDA consensus standard back on December 18, 2023, and this is notable because the FDA has oversight over medical devices. So the first place you probably want to start is to update your records on any medical device that you have that uses water to find out if the IFUs might have changed. And I have heard rumors from several people that a couple manufacturers have already adopted that in their IFUs. So I would make sure that you check on that. The other notable thing about this being a consensus standard by the FDA, that de facto makes it a best practice, and some auditors are able to justify auditing items that are consensus or best practice standards. We'll go over a typical system, and this type of system is what you might see at your facility. The characteristics of this, I named it an emergency water small volume AAMI ST108 type system. And basically these types of systems are very compact. They generally are low capital costs because most of the components are changed out on a regular basis. If you think of it like a battery, you're going to be changing it out because they'll get used up quite frequently. So you're going to have a service company largely bringing in tanks and taking out tanks. They can be very helpful for small clinics or small water volumes that are needed for medical devices. On the downside, they do have a higher per gallon cost typically. If your city water coming into your facility is good quality, you may consider taking the utility water after some type of pre-filtration. In Europe, it's very common. They'll have either stainless steel centrifugal filters or ultrafiltration systems, and that's going to remove the corrosion particulate that comes from the building water, a lot of the sediment, and even some biofilm fragments to keep this high purity water system a little bit cleaner, and obviously it helps with the utility water as well. The characteristics of this system is there's carbon filtration, so there's usually a lead and a lag tank. Think of it as one tank polishing the other. And then you generally have the DI exchange, or sometimes called demineralization tanks, which basically will get rid of most of your dissolved charged content or contaminants. Then you will go into a bacteria filter or a flushable ultrafiltration system. Because these different processes often break down the pressure coming in, sometimes it's necessary to have a distribution pump to repressurize that line, and then that often will go into a UV light for further disinfection, and endotoxin filter. Some people do put the endotoxin filters on each device, and some put that on the line going to the devices. You generally want to have this as close to devices as possible, so if it's a long line, you want to put that closer to devices rather than close to the UV. On the diagrams, if you notice, we also included the purpose of each one of the technologies in this diagram. That'll help you if you do have a problem, that you can go through and isolate where the problem might be coming from or coming up with corrective actions. I also wanted to point out that we've indicated if you have lamps complete, which allows for sensor inputs, you can automate some of that monitoring by putting sensors at the locations indicated by stars. We go to the typical high volume water system for AAMI ST108. As you can see, there's actually quite a few of the same components that are in here, but there's also some added ones. Generally, these are going to have a much higher capital cost, but they are going to provide for a lower cost per gallon of water. In these systems, and the diagram is basically exactly the same as the last one where we have the purpose for each one of the technologies. As you can see here, you want to do some kind of pre-filtration, non-media type, either centrifugal filtration or ultrafiltration. Typically, you'll go into a water softener. It's a cationic system, so it will also take out some metal. And generally, people take off the utility water after the softener in these type of systems. The reason that the water softener is before the carbon filter is just the best practice that was developed back in the dialysis system design back in the 90s, which I was involved in. And through a lot of trial and error, we found that having the disinfectant still in the water helped keep the water softeners from growing organisms. So that's why the carbon filter is located afterwards. But talk to your equipment supplier about that. They're going to validate their system and they may have subtle changes. Again, we do have on this diagram stars, and those indicate where you might want to automate some of this with sensors if you have lamps complete. After the carbon filter, this generally goes into a reverse osmosis, or RO as it's typically known, system. And then that leads into the deionization or the demineralization tanks, which are basically polishing the RO water. Again, you have a bacteria filter or a flushable ultrafiltration system that goes into a high purity water storage tank. Because the water will be not pressurized, you are going to need to have a pump to be able to pressurize that system again to deliver minimum pressures to the medical devices. Typically, you go through a UV to the endotoxin filter, and then as you can see, it's going to go around in a loop and back into the tank. One of the other alternatives of this is there's pharmaceutical copies of pharmaceutical systems that are used for this application, and there they'll use ozone generator at parts per billion, very low level. That's been proven to keep water very pure in storage tanks in Europe, and then a UV for destruction of the ozone before it goes to the devices. So you may see a couple different versions of the system, but the UV seems more common in the United States. The other very critical item that is right here is basically a vent filter. Make sure they're absolute filters and they're hydrophobic. If you get a hydrophilic one, it will wet out and it could cavitate the pump, and it's not going to do a very good job of keeping bacteria from the air from contaminating that tank. Within lamps, on training note 3.008, we have very extensive information which goes step by step and will help you walk through. In fact, a lot of the information that you're seeing, such as those diagrams, are included in the training note 3.008. What are the limits per AAMI ST108? There's 18 total limits that you'll need to consider, and 3 grades of water. One is utility water, the other is critical water, and the final one is steam, but actually you're waiting for the steam to cool to test the condensate. A lot of these parameters you're likely going to need to have an outside lab do. They're at very low levels, so they're going to need liquid chromatography or spectrometry machines to be able to do them. But there are some units or parameters here that you can do either through sensors or you're going to prefer to do using tabletop or drop type systems that are well made. So some of the items that you could automate with sensors are pH. You can also automate the turbidity with NTU, and the conductivity could be set up for automatic oversight and plugins to lamps with Lamps Complete. The items that you're going to want to test in the field are typically going to be the hardness and the total alkalinity. And the reason you want to do that as soon as you can rather than wait to put it in the bottle and send it out is there's dissolved gases in a lot of the water, and the alkalinity level can actually change, or you can get precipitation or change from carbonate to CO2. So you sometimes will see differences as those dissolved gases are pulled out of the water over time. There's also some other items that you could do. There's very inexpensive or reasonably priced pH handheld devices. You do need to make sure and keep a log of them being calibrated. Also conductivity and turbidity, there's handheld sensors. Again, the calibration is going to be the most critical one. Now the AAMI standard does mention that you could do color and turbidity with visual indications. I believe in the future they may change that, and I just wanted to let you know that anything below 10 NTU looks clear to the untrained eye. Dr. Spencer has a very nice chart. His text produced by WEF, or Water Equipment Federation, that explains this, and NTU is a much more objective visual test. The cities itself, the municipal cities, need to prove that NTU is less than 1 95% of the time. So since visual inspection is so subjective, if you ask 7 people, you're going to get 7 different estimations, with most of them not being able to see below 10, you're missing a lot of indicators that could be explaining corrosion happening in the system or potential microbial growth going forward. What are some of those contaminants in that list and the issues with sterile processing? I thought this would be helpful. This has come up in a couple questions I've had with hospitals in the last couple months. I just made this small chart that should be helpful. Basically, with scale and alkalinity, this could affect the sterile processing devices by clogging the nozzles and the piping, so you're not going to get sprays or cleaning done very well. It also will reduce the heating efficiency, so you might not achieve the heating levels that are needed for sterilization or for effective hold times. It also reduces the efficacy of detergents and chemicals. They react with those chemicals. A famous one is alkalinity and oxidants. They actually can help neutralize some of the oxidants like ozone in food and beverage processing. And then you also have scale with biofilm, which can protect microorganisms, and that actually is almost as insulating as a layer of polyurethane, which is used to insulate your building's pipes. Another contaminant of interest, or group of contaminants, are silicates and phosphates. A lot of these have either weak or no charges, so they tend to go right through a demineralization tank. And they have very similar issues to hardness in the equipment. They can build up over time. They can create basically a glass-like layer on items or cover up areas. And they also can create coatings that are not visible, so you might not even be able to see it. That's why those particular contaminants are being at the levels that they are. The other item, the metals, if you notice, those are the items that are at the lowest levels that are likely to be sent out to a lab to test. Metals have a lot of effect with what happens to detergents and sanitizers. It immediately produces galvanic corrosion. So even on stainless steel, if you have certain metals, you can create galvanic corrosion. It also can contribute to instrument malfunction, especially movable instruments like scissors and other items that are moving. The metals can interfere with their function. It also can react with patients or solutions if the accumulations on the instrument of certain metals, when it's put into the human body, it actually can react with either what's being used in the procedure or with the patient themselves. Some people are very sensitive to metal. Another area of concern is chlorides, and chlorides are very easy to detect if you're having a chloride issue because it induces pitting. It almost looks like pinhole worm kind of intrusions into metal, and that type of corrosion is irreversible. It cannot be removed by cleaners or acids, so it's a high concern area. And of course, microorganisms, we're dealing here with direct contact with patients, and you need to make sure that you're not producing infections or contaminating devices. The endotoxins basically can create negative consequences via pyrogenic responses of fevers or complications with already stressed or immunocompromised people. And finally, the pH levels are important because low pHs do corrode metal. They increase scaling at high levels. They also can convert alkalinity into carbonic acid, which will also add to scaling. And pH also greatly affects detergents and sanitizers. A very good way of demonstrating this, if you look on the CDC chart for pools, they basically show that at pH 8, free chlorine only has 27% of disinfection capabilities, whereas if you go down to 7.2, so not even a full number down, the majority of the chlorine level is going to be able to disinfect or kill microorganisms. I also thought this chart would be very helpful for you. Not everything gets sterilized as easily as other things. So there is actually a hierarchy on what is more difficult or what could be more effective. You could think of you have some metals and you get 80% of the sterilization done, or 70%, or 95 instead of 100% of the validated cleaning done. Different things can pop up as surviving that sterilization or cleaning process. So on the bottom of this chart, you'll see that the easiest ones to inactivate or sterilize are basically lipid-enveloped viruses, followed by gram-positive bacteria. Now we're getting more difficult or more resistant. Fungi are the next ones, and then you have your gram-negative bacteria, which includes a lot of the opportunistic plumbing pathogens. Non-enveloped viruses are the next most resistant to sterilization. And then you have mycobacteria and cysts, which have coatings on the outside. That's why they're more resistant than a lot of their other type of organisms. Spores, and finally the hardest to sterilize or to inactivate, are basically prions. If you're not familiar with prions, where I live in Wisconsin, there's actually a huge concern about transfer from wildlife, from deer who have these prions. It's a wasting disease being transferred to humans in the future because a lot of people do deer hunting and are in contact with deer eating out of their bird feeders and things like that. So what needs to get done? If you want to move forward with getting set up for ST108, I think the first place to start would be to look and include all the new AAMI roles in your water management team. The standard, the AAMI standard, not only has the water quality, but it also adds roles that need to be on the water management team. And you need to have a water management plan for any area that has this quality of water. So another thing you might want to consider is make sure that you have water management plans for your surgery centers, or even some of your outpatient surgery centers and other areas where you might have autoclaves or endoscopes. The second thing you'll need to do is update your plumbing diagrams to include sterile processing devices and the water systems associated with it. One of the ads there for the roles is your clinical engineering department. They need to work with IP to basically update the risk assessment and possibly the WIC reforms as well. You might have new areas that you need to incorporate as far as being affected by water and rate risk. The fourth thing that you'll need to do is you go into the documentation area and you want to set up a folder for device images in labs. AAMI also requires that you have visual inspection of instruments, and you need to keep documentation of those inspections or images in any kind of audit. So it would be very helpful to have that set up as a folder, and as you are taking pictures, digital images are very easy now of instruments when they go through the processor for documentation purposes. You can keep that in labs in that folder. And then finally, you'll want to set up your target limits for the devices in labs. A little discussion on the water management team roles that AAMI requires. I thought this would be helpful. I used a check mark for ones that typically people already have in labs, and boxes as a checklist for the ones that are going to be needed to add if you don't already have them. They do call out a top organizational leader. This would be an executive sponsor, typically someone in the C-suite. They have the authority to make critical decisions regarding water restrictions or other emergency response measures. They also are able to allocate necessary resources, whether that be financial or personnel. Facilities engineering staff, typically everyone already has that. I assume a lot of you are on this call. Infection prevention, if you don't have them on the plan, they definitely need to be involved on your water management plan and an active part of it. There's quite a few things that they need to do. They're going to need to manage the policies, procedures, protocols, quality assurance programs. That includes patient surveillance, so post-surgery surveillance, developing corrective action plans, assessing risk, and escalating issues to leadership when needed. The medical device processing personnel, so these are the people that are in the sterilization area, they need to be included. These individuals possess knowledge about water usage within the device processing areas, such as sterile processing. They monitor processing equipment for any damage, discoloration, or issues related to water quality. These people are likely going to be uploading a lot of the photos. Your clinical engineering staff that's going to need to be added to the water management team will handle risk management, equipment procurement for water treatment, and their responsibilities encompass risk assessment, incident investigation, project management, capital planning, and construction. Then you also need to include personnel in the surgical suites or procedure rooms. I'm not sure if you're aware, but generally they do kind of a second check of the instruments before they're handed to a surgeon. Their duties involve visual inspections, monitoring procedural responses, and assessing instrument functionality and assessing the surgical site infections. And finally, you're going to have water treatment specialists. These are typically going to be high purity water treatment specialists, maybe someone that knows quite a bit about your dialysis systems if you have those. And it could be an outside consultant, but typically in large organizations, they're going to have someone that has specialized in this. And they are responsible for selecting, integrating, qualifying, and validating the water treatment equipment that is at the facility.